Good day, students. In this clip, we're going to be going over how to expand binomials. We are going to be making use of the Pascal's triangle and the binomial theorem. All right, so let's write down the instructions for example 1. So for example 1, we are to um, expand the given binomial using the binomial theorem. And then we're going to verify the results with a different method. Okay, so and verify your result. Verify your result um, using Pascal's triangle. All right, so there are two methods of expanding binomials. We can use the binomial theorem and the Pascal's triangle. And in some cases, one method might prove superior to the other method. In some cases, there are no difference. So we're going to look at a situation where it's kind of in the middle as to which method is much more uh, advantageous to implement. All right, so the binomial under consideration is 3x minus 5y to the third. 3x minus 5y to the third. Okay, so we're going to start off by writing down what the binomial theorem is. So the formula for the binomial theorem is as follows. If you want to expand a plus b to the nth power, it's given by the discrete sum from k equals 0 to n of the combination of n choosing k at a time, n choose k, of a to the n minus k times b to the k. All right, so this is the combination notation. All right, another way that this can be written, this can also be written as a summation from k equals 0 to n. Instead of n choose k, we can use a formula for combination, which is n factorial divided by n minus k factorial. This is permutation, but we just add a k factorial piece here, it becomes combination. Okay, times a to the n minus k, b to the k. All right, this is much more explicit. It tells you exactly what to do to determine your coefficients. All right, so we're going to implement this formula in generating the expansion of these binomial. So what you want to note is that for this formula, n is always um, constant. N is the power. Okay, so n is 3, but the value of k varies. Okay, it goes from 0 to n. In this case, that means it's going to go from 0 to 1 to 2 all the way to 3. K is going to assume these three values. All right, so in our formula, n will stay the same, but k constantly changes. So any expression that involves k, that term will vary throughout the generation of terms of the expansion of this. Okay, so let's start by computing the term where k is equal to 0. Where k is equal to 0, um, we know n is constantly the same, so in that case we're going to have um, 3 choose 0. That's when k is equal to 0. And then let's go with k equals 1. When k equals 1, we're going to have what? 3 choose 1, because remember n is always constantly 1. So this will help us find the second term. And then when k is equal to 2, you have 3 choose 2. All we are using is we're using the values for k. So k is 0, 1, 2, 3, 0, 1, 2, one more. for k equals 3. Let's go ahead and write that down. For k equals 3, we have 3, choose 3. All right. So what I've just listed is the combination piece of the formula. This piece right here, I've just listed all four for the 4 terms that we're going to have. Now I'm going to start doing this piece, the a to the n minus k, b to the k. All right, so that's pretty easy to generate. In this problem, just to make sure you understand what's going on, a is going to be 3x, and then b is going to be negative 5y. You notice in the formula you have plus, so if we express this as a sum, then we have to associate this minus, group it with the second term here. So b is negative 5y. All right? So please keep that in mind. This sign is really important. So we are going to do a to the n minus k, so this would be a is 3x, so we'll do the 3x raised to the n minus k. 3 minus 0 is just 3. And then for the next one, we're going to have 3x raised to the 3 minus 1, which is 2. And then for the next term, you see a pattern here? It's descending, right? 3x to the 3, 2, what do you think this is? 1. And then this one, 3x to the 0. All right? So this pattern always happens when you're using the binomial theorem. And then for the b term, b always takes the value of k. Okay, so b is going to be negative 5y to the, what is k? Here, k is 0 to the 0. And then the next term, when k is 1, we're going to have negative 5y to the what? To the 1. And then when k is 2, negative 5y to the second. And then lastly, negative 5y to the third. Now, if you do it in column approach like this, is much easier for you to generate the terms. And now, just to check your work, the sum of the exponents of these terms to the right of your combination expression should be, the sum of the powers should be 3. So 3 plus 0 is 3, good. 2 plus 1, 3, good. 1 plus 2, 3. 0 plus 3, 3. Perfect. This one descends, 3, 2, 1, 0, and this should be doing the reverse, 0, 1, 2, 3. All right? So when you're generating a lot more terms, please let the pattern guide you, okay? So this one should be descending, and this should be ascending, okay? All right, now let's work this out. Now we're going to use the combination formula that we use here to determine the value of these combination expressions, okay? So 3 to 0 is simply 3 factorial divided by 3 minus 0 factorial. That's n minus k factorial, 0 factorial. 3x to the third, 3 to the third power is 27, x to the third. Anything raised to the 0th power is just 1. That becomes 1. And then if we simplify this further, we'll have 3 factorial. We do not have to break this factorial expression down because in the denominator we're going to have 3 factorial here, and 0 factorial is just 1. Okay? In most cases, you always have to break the bigger factorial and stop at the factorial term that matches the smaller. So since these two are identical, there's no need to break them down. Okay, so this times 27, x to the third. And the first term in the expansion of 3x minus 5y to the third is 27 x to the third, because these two divide out to just 1. Okay, these two identical divide out to 1. All right, let's move to the next one. For this one, we're going to have 3 factorial divided by n minus k, 3 minus 1 factorial times 0 factorial. All right, 3x squared. Remember, you're squaring the 3 and the x squared, so it's going to be 9x squared times negative 5 to the first power, which is negative 5, y to the first power, which is y. Okay, now let's work this out. This one, you're going to do some work here. You have 3 factorial over 3 minus 1 is 2 factorial, so I express this as 3 times 2 factorial stop. Why do I stop at 2 factorial? Because the smaller factorial and the bottom is 2 factorial, so we'll stop there, okay? 0 factorial is 1. 9 times 5 is 45, so we have times negative 45 x squared y, okay? And then when we work this out, these two cancel out. That's why I stopped at 2 factorial, so they cancel out. 3 times negative 45 is negative 135 x squared y. That's the second term in the binomial expansion. Now the third term, we're going to have 3, which is 2. That's going to be 3 factorial over 3 minus 2 factorial, 2 factorial. Okay, I made a mistake up here, but kind of cancels out. That's supposed to be 1 factorial. Sorry about that. 1 factorial. The reason why I didn't mess up my answer is because 1 factorial and 0 factorial are the same thing, so that's 1. Okay, so that's straightened out. So we have 2 factorial here times 3x to the first power is just 3x. Negative 5 squared is going to become positive 25y squared. All right, let's simplify this. How do we do this? Now we have 2 factorial down here, so we want to break this down to 2 factorial because it's the smaller factorial of the 3. All right, this is always smaller, so you're going to have 3 times 2 factorial, stop, over 3 times 3 minus 1. 3 minus 2 is 1 factorial times 2 factorial. These two cancel out. And then we're going to have, let's see, that's 3, it's going to be 3. And then 3 times 25 is 75. 75 is going to be 75 xy squared, so 75 xy squared. And then if you multiply 3 by 75, you have 225 xy squared. Alright, if you notice there's an alternation in sign. This is positive, this is negative, and this is positive. What do you think the last one is going to be? It's going to be negative. Okay, so whenever you're expanding binomials where the sign is between it is minus, there's always going to be an alternation in the sign of the terms. So that's another way to make sure your work is accurate. So applying the combination formula to this term right here, we have 3 factorial, that's n factorial, n minus k, 3 minus 3 factorial, times k factorial, 3 factorial. 3x to the 0 is simply 1, as we did up here. Negative 5 to the third, 5 times 5 times 5 is 125. But if you raise a negative sign to an odd power, it preserves the negativity, so negative 125y to the third. Okay, let's go ahead and evaluate this factorial expression right here. We're going to have 3 factorial over 0 factorial times 3 factorial. Okay, times negative 125y to the third. Now 3 factorial goes here 1, 3 factorial goes here 1, and 0 factorial is just 1. So our final term is simply negative 125y to the third. Okay, so let's write out the binomial expansion. So we have 3x minus 5y to the third, when expanded, is 27x to the third minus 135x squared y plus 225xy squared minus 125y to the third. So that goes your final answer using the binomial expression, binomial theorem. Okay, so now let's use the Pascal's triangle, and then we can have you choose the one that you think is much effective for this problem. So Pascal's triangle. We're doing the same problem, okay? So let's call this method 2. Pascal's triangle. So for Pascal's triangle, The limitation basically exists in the generation of the triangle. If you can generate the row of the triangle um, at a reasonable amount of time, then it's much more beneficial to use the Pascal's triangle, as you will see momentarily. So we are working on 3x minus 5y to the third. How many rows are we going to go? The power of a binomial expression tells us how many rows. Since we're raising this quantity to the third power, we're going to go down as far as 3 rows. Okay? All right, now let's set it up. We have 1 as the 0th row. 1, 1. Row 1, 1, 2, 1. Row 2, 1, 3, 3, 1. This is the third row. Row 3. Okay? All right, so what this row does, it basically generates the output of these computations right here. You see all this work we're doing over here? This Pascal triangle does exactly the same thing, but it does it easier. So let's stack up the terms of the third row of the Pascal's triangle. 1, 3, 3, 1 in order. Okay? And now we're going to go the first term, 3x, raise it to the third power. And then the second term, negative 5y, raise that to the 0th power. And then we're going to start to do the switcheroo with the powers. So this power descends to 0 and this ascends to 3. Okay? So first step, this one descends down to 2. This ascends to 1. Let me move this up a little bit. It's weirdly spaced, so let's put it closer. 1, 3, 3, 1. Okay, so this one descends to 1. This ascends to 2. This descends to 0. And this ascends to 3. Alright, you know you're done when there's a complete reversal of the power. So this was 3, 0. Now you have 0, 3. You know you're done. So what you're going to do now is simply expand the term and find the sum, and that's it. Okay? So 3x to the third, this is 1. Let's not waste time with that. This is 1 also. 3x to the third is 27x to the third. 3 times, so this becomes 3 times 9x squared times negative 5y. So 5 times 4. 9 times 5 is 45, times 3 is negative 135, x squared y. And then let's work on this. 3 times 3 is 9, 9, so let's write it out. So 3 times 3x times minus square is positive, right? So this is 25y squared, which equals 9 times 25. 9 times 25 is 225 xy squared. And then last but not the least, negative 5y to the third is 5 times 5 times 5, which is negative 125 y to the third. All right. So our final answer, the expanded form of 3x minus 5y to the third, is simply the sum, 27x to the third minus 135 x squared y plus 225 xy squared minus 125y to the third. All right, and that's, let's see, that's exactly what we had before. So we can see that the answer is correct. So which method is quicker? We can clearly see that the Pascal's triangle is much faster in this example. But what if we were finding the 50th expansion, the 50th power? Okay, so if we wanted to use the 50th power, we can compute the terms directly using a calculator in this method right here. But if you wanted to generate the 50th row of the Pascal's triangle by hand, it's very, very difficult and time consuming. So for lower rows, let's say the rows goes as high as 4 or 5, you can use the Pascal's triangle, that's faster. But when it starts to get to higher rows, then the binomial theorem is much faster. Okay, and also when you're looking for just one term in a row, you don't need everything, then the binomial theorem is also much faster and effective in that approach. So that's basically it. So thanks so much for taking the time to watch this presentation. Please feel free to subscribe to our channel for updates to other cool clips such as this. Please post a comment to let us know what you think. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.